Good afternoon. I'm Les Ferrani. I'd like to demonstrate a method of deriving an expression for the gradient in spherical coordinates. There are numerous methods of doing this, but generally they involve some graphical construction, visualization of distances, or some way of proposing a formula for the answer and then working backwards. I'd like to show a simple method that involves little more than mechanical substitution of expressions that we already know. A little bit of high school algebra, but generally the steps involve not much more than inspection. So writing the gradient in Cartesian form is very simple. It looks like this. But unfortunately, if we have a system of spherical coordinates like this, the gradient does not look like this. But we know that the first expression, the Cartesian one, is true. So if we could just simply substitute the values of the unit vectors I hat, j hat, k hat as expressed in spherical coordinates and then do the same for the derivatives, we'd pretty much be done. However, getting those quantities is not that straightforward. But if we have a clear picture of the coordinate system we're working in, namely the spherical system, it's easy to draw a vector from the origin to any point, and we know that it can be expressed in Cartesian coordinates like this. And if we've worked with the spherical coordinate system any more than a little bit, then we can easily translate the x, y, and z vector components into expressions in as functions of r, theta, and phi. But then, of course, we still have the unit vectors. However, the unit vectors, as expressed in Cartesian coordinates, namely the ones that we use in spherical coordinates, are easy to find. The radius vector itself simply is a product of the magnitude of the vector and a unit vector. And it's pretty easy to find the other two unit vectors, theta hat and phi hat, because theta hat is really just what happens to the unit vector as we keep the other quantities constant. So in other words, we're just taking the derivative of r hat with respect to theta. And similarly, to find phi hat, since phi hat is always of unit length, even though we may be describing motion in the xy plane or any plane parallel to it, to the xy plane, we find that the diameter of a horizontal cross section becomes much smaller as we move upwards in the sphere, and finally it disappears. So the circumference, the radial circumference of the sphere is not constant, but the unit vector is. So really, we can choose any plane, and the simplest one is the xy plane itself, in which case all we need to do is take the r hat vector and set the sine theta values to 1, because the angle, the polar angle, in other words theta, of the xy plane is pi over 2. So then, having done that, all we need to do is ask, how does this expression change in the phi direction? So we get these three vectors. It's easy to see that they're all unit vectors just by taking each one and calculating the scalar product of the vector with itself, remembering that sine alpha squared plus cosine of alpha squared is 1 for any angle alpha. But we can write these three vectors in matrix form. So when we do, we find a thing that looks like this. And wouldn't it be nice if we could just invert this matrix? Instead of saying r hat, theta hat, phi hat are some function of I hat, j hat, k hat, do it the other way around. And this matrix expression is nothing but a quantity on the left is equal to a matrix times a quantity on the right. So why wouldn't we just divide the quantity on the left by that same matrix, and then we'd have the unit vectors we're looking for, all in terms of the spherical quantities. Well, inverting a matrix is not a simple thing. There's a formula to do it, and even if you remember it, it's a very tedious process in general, with some exceptions, and luckily this is one. This is an orthogonal matrix, and in fact its inverse is just its transpose, which means that we look at the main diagonal from top left to bottom right, and we reflect all the elements of the matrix about that diagonal. So in fact, we can easily come up with the inverse matrix, and hence the expressions for I hat, j hat, k hat in terms of r hat, theta hat, phi hat. But that's only half the problem, because going back to the gradient that we're looking for, we need to do essentially the same thing for the derivatives. Now, it's a simple matter of applying the chain rule to write down what those derivatives are. But again, what we have here are derivatives of Cartesian quantities in terms of derivatives in the spherical quantities, when in fact we're looking for the opposite. And again, we have a matrix that needs to be inverted. But in this case, the matrix is not orthogonal, so we can't do the same thing that we did before. However, we can break this matrix up into a product of matrices if we know a simple rule that allows us to change the values of one row or one column at a time in a matrix. And in fact, it's done by taking a diagonal matrix, changing one element along the diagonal, and then by pre-multiplying a simpler matrix factor. By pre-multiplying some matrix, we come up with our original matrix. And in fact, the matrix we want to invert has the factors r in the second row and the factor r sine theta in the third. So we can decompose this matrix into a product of two matrices, and when you know it, one of them is the one we've already seen. So the other one, as promised, is a diagonal matrix, and it so happens that diagonal matrices are even easier to invert than orthogonal ones, because in fact all we need to do is take the reciprocal of each element along the diagonal. So what we now need to do is invert the product of these two matrices, and we have to know that the inverse of a product of matrices is the product of the two matrices in reverse. So what we end up with is the two easily inverted matrices, and all we need to do is multiply those two. And once we do that, we come up with this expression. So now we can go back to our original Cartesian expression for the gradient. We can substitute the values we find from these two quantities, and after a little bit of algebra, which is not punishing, and keeping in mind especially the identity for sines and cosines that we used before, sine squared alpha plus cosine squared alpha is 1, that helps us a great deal, and finally we simplify to this expression here. And I hope you have occasion to try this at least once. It's quite flexible. It can be used for other coordinate systems. And it's a good thing to have in your back pocket in case you have to write an exam and you forget your cheat sheet. Thank you very much. Stay tuned for more interesting tips. Please feel welcome to comment on or ask questions about this video, and above all, to like it. Thank you very much.